Hi, ladies and gentlemen. Today I'm talking about method of designing and simulating photonic modulator on Lumerical. So my name is Majid. The outline of my talk, first of all, I will discuss about um, optical transceiver, and then I will go to the more detail in optical modulator, part of optical transceiver. And then I will compare three modulators, actually electro-absorption modulator, Mach-Zehnder modulator, and microring modulator. So then I will show you how we can design and simulate this kind of modulators using Lumerical and Ansys tools in both component level and circuit levels. So regarding to the silicon photonics, because optical transceiver is a part of data and telecom. So if we see the roadmap for silicon photonic, we see that in 2025 we need to reach 25.6 or 51.2 terabit per second with the co-packaged optics. And why do we need such huge bandwidth? Because actually, because of the demand, our cloud service, our industrial automation, video streamings, and also because of the emerging of new technology like augmented reality, virtual reality, and also connected car to the internet and Internet of Things. So everywhere that we can see that people need the bandwidth. So for this reason, some companies like Cisco, for instance, created a photonic electronic circuits like this. As you see here, this is a photonic electronic chip. So here is a electronic IC. This one is the blue one is silicon photonics, and you see here this is a light source and fiber array. So and also, for instance, regarding to the co-package optics, you can see some IC from Intel and Rockley Lab that they are working on this area. So, but what is the key trend for optical transceiver technology based on our demands? So, as you can see here, we have pluggable optics. So most of companies work on pluggable optics. So in pluggable optics, we have some benefits like support multi-vendor. So we support, it has quite flexibility, and but because of the SerDes power, we have some limitation, and we expect we achieve in this trend, for instance, in 2025 to 1.6 terabit, but very difficult to increase the bandwidth because of the nature of electronics. So SerDes power and electronics mobility, electron mobility is a barrier for this technology. So for this reason, we need go to the, for instance, onboard optics. So in onboard optics also, as you see here, for instance, we expect in 2027 we can achieve 3.2 terabit per second. But as you can see in the co-package optics, especially in silicon photonics, we can dominate to these barriers, and we expect, for instance, achieve 6.4 terabit in 2030. So most of companies working on co-package optics in silicon photonics area, and they are working in this area. So the optical transceiver that I'm talking to for today, so it's focused on this area. So this is the example of Intel optical I/O. And so they are using a co-package optics, for instance, in 2020. So as you see here, for instance, in 2016, the Intel in the pluggable module, we have 100 gigabit per second. But for 2020 demo of Intel, we can achieve 1.6 terabit because of the actually because the photonics and electronic circuits is fabricated near each other, and for this reason, if you look at the electrical paths, you can see that the much, for instance, here the size of electrical paths is around centimeter. Here is around inch, and here, for instance, in the future that Intel want to achieve for these technologies around millimeters. So, for instance, this one also an example of AR lab that they are working on optical I/O. So, because today we're going to talk about photonic transceiver, and so what is the actually this technology? As you see in this picture, we have a laser, we have a modulators, so we have transmission medium, we have photodetectors. So as you see here in the modulator side, we have electrical signal. The electrical signal comes to the modulators, and the modulators, as you see in this picture, the electrical signal is carried out by the optical signal, and then in the photodetector side, it converted to the electrical side. So, and also in this picture, you can see quite easy. For instance, the blue one is a light, and this one is electrical signal, and you can see that the electrical signal is carried out by optical signal. So today we are going to focus on photonic modulators. Actually, optical modulator, photonic modulators, there are some merit of interest for this kind of application, because we have an electronic chip and we have a photonic chip. In the electronic chip, we have a driver swing that must be quite compatible with CMOS, and in the photonic side, we have some limitation in bandwidth, you see in for instance optical modulation amplitude. So we are working to improve this kind of characteristic in numerically. So regarding to different modulators, for instance, we have electro-absorption modulator. It depends that which application we use in our technology. For instance, in electro-absorption modulator, you see that the bandwidth is high, driver swing is low, is good, thermal sensitivity is low, is good, so area also low. But the problem for this modulator is the O band. So we cannot use this kind of modulator in the O band that we in the O band also it's important for us. So if we want to work in O band, so we cannot work on electro-absorption modulator. But for if we look at the Mach-Zehnder modulator, we can see that the driver swing is high and the area also is high. So for the application that we don't need the compact device, so this opportunity, for instance, this modulator is good. So for the microring resonators, the modulation driver swing is good, but the problem is thermal sensitivity. So sorry. So because this device is very sensitive to the thermal, but there are also a consideration in thermal management that you can find in a lot of application and in literature in the that published with scientific institute and industries. So So let's start with electro-absorption modulator. Uh, Electro-absorption modulators, actually the physics behind the electro-absorption modulator is quantum-confined Stark effects. So as you see here, for instance, in this picture, we have indium gallium arsenide and gallium arsenide, and it's a kind of heterostructure semiconductor. So in the gallium arsenide side, both we have confinement in holes, electrons as holes, because a lower band gap, and also confinement of optics because of a larger refractive index. And this gives us a good opportunity for to work this kind of modulator. So if we connect a voltage source to this modulator, we can see that our band edge is tilted. So because the electrons actually attracts to the positive holes, and the holes goes to the negative holes. So for this reason, our also density of a state, the peak of our density of a state also is shifted. So here we have an absorption versus wavelengths for V dot in connecting the voltage source, and with connecting the voltage source. So as you see here, these are actually excitonic peaks, and when we apply the voltage, we can see that our excitonic peak is shifted to the actually redshifted, or to the longer wavelengths, and this is because of the actually as you can see here, the electrons can comes to this level, and because this level, the energy level of this point by this point is same, so we can tunnel to the conduction band. So this is a theory of electro-absorption modulator. And also extension ratio, it depends on confinement factor and absorption coefficient. So I will show you how we can calculate these parameters using numerical tools. So, but how we can model electro-absorption modulator? We can use, for instance, a quantum dot. So as you can see here, when we connect a voltage, we can see that our absorption is much lower. And also, if we like our previous example, if we have a quantum well or graphene, we can see we have a redshifted. And also another idea is using excitonic peaks. As you see here, when we apply the voltage, our excitonic peak is removed, or using precarrier effects. So what is the workflow of Ansys for designing of electro-absorption modulators? So the workflow is started with numerical mode. What we can calculate with numerical mode, we calculate effective index and overlap with gain region. And this case, we can calculate the modal properties like effective index, group index, and mode confinement. And also in numerical charge, we can calculate absorption coefficient and transmission as a function of applied bias voltage that I talked in my previous in theory part. So then in the numerical interconnect, we can connect this component together, and we can calculate a modulation response. The basic of actually electro-absorption modulator basis is in this site. You can go to the Ansys Lumerical website, and this is gas electro-absorption modulator. You can download the file, and I will show you the different results of this part. But before that, if I want to talk about the structure, this is our device model. So as I mentioned, we are using a quantum well. So we have 2 wells and 3 barriers, and we have a gallium arsenide and superlattice. I will describe what is a superlattice in our structure. So for the electro-absorption modulator, we have a different solver. So the first solver is charge. And the charge, actually, with you in the charge, we can calculate the. Actually, it's based on the finite element method, and it solves the Poisson continuity and drift diffusion equation, and supports electrical contact doping bulk semiconductor, and so also support a different heterostructure material. And regarding to the multi-quantum well, actually multi-quantum well, it's a kind of gain solver. It solves the Schrödinger equation, and you can calculate the gain and the spontaneous emission. I will show how we can do that. So this is the coupling through the complex optical media, optical index. Actually, in numerical charge, we have a charge, and we have multi-quantum well. That this is self-consistent solver in the numerical charge, and the output of this goes to the numerical mode FDTD, and we can use in other software. So, and also charge and also heat included in this chart. So this is the numerical mode. So it's very user friendly. It's very easy. It's handy. So you can define your material here very easily, and you can actually insert any structure that you want, you need, and so for the simulation side, we need to actually first we need to define our structure. So here, because I defined before, so this is our structure. As I mentioned in this slide. So this is our structure. So I want to design this structure in numerical mode. So you can see we have a gallium arsenide on top. We have superlattice and a multi-quantum well, and a different material. And also, for instance, for the gallium arsenide, you can right click on the gallium arsenide. You can go to the edit object. You see the material, and for the multi-quantum well, you see, for instance, a different part. Barrier 1, well 1, barrier 2, well 2, barrier 3. So it's very handy. So the first step in numerical mode, you must design your geometry. The next one, you need to include the solver. Our solver is FDE in numerical mode. So in FDE, you can define your geometry, your mesh seeding, and the boundary condition that you need. For instance, I use the medal boundary condition, and I in my video I describe why we use the medal. So please follow the video for more details, and the material why we need conformal variant. I describe it, and so and also you can see another mesh here, because for the quantum well, we need a fine mesh, more accuracy mesh. For this reason, we added another mesh. So, so now, based on our slides, so we need to calculate effective index and overlap with gain region. So if you go to the numerical mode before I calculate before, and to save the time, after running the simulation, you can see that sorry, I catch a cold, I think. Yeah. And when you run the simulation, you can find a different mode. So we want to focus on the first mode. So you can see the effective index, wavelengths, loss, and the effective area, and also you can go to the frequency analysis, and here in the frequency plot, you can plot the effective index, loss, gain, group index, group velocity, and different parameters versus wavelengths. So, and regarding to this part overlap with gain region, if you go to the for instance, sorry, to the here analysis, power and impedance integration. Here, I said in the multi-quantum Weyl region, just calculate the confinement factor, and the confinement factor is around 6%. So after that, actually, we can extract the file that we need to the numerical charge. For this reason, also, if you go to the model and edit object, you can see that our output file name is QCSE electro-absorption modulator. And if you go to the script, you can see that I actually saved an effective VG and fraction integrated in this file. So I need to insert this file to the numerical charge. So please, if you have any question from numerical mode, I'm very happy to answer your question, and otherwise I can go to the numerical charge. So, okay, so let's go to the numerical charge. Yes. So the numerical charge is the same as the, so let's close these two windows. So in numerical charge, we have actually this is the environment of numerical charge. So we have we can define our material here, our geometry, for instance. But the difference between numerical charge, the material in numerical charge and numerical mode, is that in numerical charge, if you go to the electrical and thermal, for instance, if I select a gallium arsenide, for instance, gallium arsenide, and you can see that we have electronic properties, and for instance, DC permittivity and effective mass. And if we go to the effective mass, we can see that our effective mass, it depends on the temperature also, or band gap is depend on the temperature. And also recombination, we can include a different recombination, like Shotcrete hole, Auger, radiative recombination. And also in thermal property, we can include the thermal property of gas in our definition. That's so for this reason, numerical charge support multi-physics actually. So for this reason, you can see a different property like optical property and thermal property. Yeah, and also here is our geometry, and so similar to the numerical mode, we have we can define our material, our geometry, simulation. Then we define our simulation region. So we because we want to focus on charge, so as you see here, we include the charge definition. So in the charge, sometimes you need to, for instance, connect your structure let's go to the, for instance, go to the geometry in more detail. Here, this is the difference here. Just we have added anode and in cathode. So other material is the same. So we have anode, then we have gallium arsenide, like the structure that I showed in the actually other section. So here is our cathode. So just we need to connect the voltage to our anode. So in the anode part, if I go to the anode part and select the anode, and here we can set, okay, we want to have a steady state simulation. So change the voltage from this value to for instance, to -10. And our cathode is the constant value. So we change the anode voltage. So then after changing the anode voltage, we want to see what's going on to the actually band structure and transmission and absorption. So let's run the simulation and see the results. I think yes. So after running the simulation, just for a starting point, we can go to the band structure and we can see the result of band structure simulation. So in this part, I want to show you if we change our voltage, what's going on the band structure. So let's remove the EFP and EFN and EI. So so then if we change the anode voltage, we can see that then we changing the voltage, our band structure is tilted. So you see the quantum well, and we remember that here is our P and PIN, yes, P, and here is our N side. So here is gas, here is indium gallium arsenide, and indium gallium arsenide, and gallium arsenide, yes, and also our quantum well here is gallium arsenide, and here is indium gallium arsenide. So it's quite handy, and you can see what's going on in the band structure. For instance, for the multi-quantum well efficiency, if I go to the visualize, a new visualize, and change this to line and select this is for wavelengths, and select put it at the X, set it as X, and then go to the change the wavelengths to micrometer. So you can see, for instance, if I remove the TM, just focus on TE, you see that this is our absorption versus wavelengths for the case of we do not connect any voltage. So now if we change the voltage, so let's change the voltage. So if I change the voltage, it increase the reverse voltage. So you can see quite easily, you can find that our excitonic peaks is shifted, is redshifted, and also remember that when we talk about these schemes, so as you can see here, because of our absorption is redshifted, so we can use this phenomena to to design electro-absorption modulators. So for the if I go to the Lumerical charge, you can find that here in the Lumerical charge, this is the input file that I brings it from Lumerical mode. So, but and also there is a Lumerical charge, and also all of the Lumerical tools support a scripting language. So, for instance, here. You can find, okay, for instance, I insert the file from previous section. I want to just plot the multi-quantum well for 3 voltage, for instance, 3 bias, and I want to plot the absorption and the transmission. I describe more detail in my YouTube videos, and you can follow it in more detail. And after running the simulation, you can see that it's, for instance, for different electrostatic fields, that you can see that what's going on the transmission and absorption. Yes, this is for versus lambda. This is transmission versus lambda. This is the absorption versus lambda. And this is transmission versus energy level and absorption versus energy level. So, and easily I said, okay, convert and export these results to this file. And I want to show you this for how we can use this file in Lumerical interconnects. So now, if you look at our actually previous section, our slide, so we can use Ansys mode to calculate the different parameters, and then using a numerical chart, we calculate the absorption and transmission. And finally, we want to use Ansys interconnect. So in Ansys interconnects, you can see that in Ansys interconnects, so here I bring the component from our previous section. Actually, if you look at this file, so let's go to so this is environment of Lumerical interconnects. So in the Lumerical interconnect, we can create a circuit. So we have a different source, we have a different modules, passive waveguides. For instance, in this specific case, we have S parameters, and our S parameters, for instance, we can bring it here, and easily you can import your file into the S parameters. So if I go to the S parameters, so and so this is a general properties, and then you can see here electro-absorption S parameter data, and this is the file that is generated from Lumerical charge. Now, we want to connect a electrical signal to our modulators. So as you see here, we have a pseudo-random 25 gigabit per second, and we have a non-return zero format. So we have oscilloscope here, and then we have a continuous wave lasers, and also another oscilloscope connected to the continuous wave. So because we want to see what is our lasers characteristic, and then the output we connect to oscilloscope 1. So let's run this simulation, just because if you remember, the bias point is very important for the optical modulator. Actually, by using by changing the bias point, if you remember, when we change the bias point, then our absorption characteristic changes. So for this reason, we can change this parameter and we can see what's going on the output. So let's run the simulation. Yes. So if I display results, so this is our non-return zero format. And then if I show the results of this one, so let's start with lower voltage, because lower voltage is better for a start. For instance, with -4. -4. So I change the bias to -4 and then run the simulation. So you can see the nice, this is our electrical signal and this is our optical signal. Our optical signal followed the electrical signal. And you can calculate the bandwidth and other parameters. Now, if I change to, so let's so take a picture of this for -4 bias, reverse voltage. And now if I change the voltage to -8, for instance, and run the simulation again, you can see that there is some saturation behavior in the output. You see here, and this why there is a saturation, because if you remember, we have a linear. If we plot the transmission versus wavelengths, the best bias point is the middle of our linear region. So if we go to the, for instance, higher voltage, so our AC signal is saturated. So this is the whole story. So, and also, for instance, regarding to the ring modulators, so the same idea in the ring modulators. So we can, for instance, here we can calculate the S parameters with Lumerical FDTD to calculate the power coupling coefficient in the coupling region. I will show you also Lumerical FDTD. It's not a bad idea. So let's start also with ring modulators for Lumerical FDTD. So this is actually a general view of Lumerical FDTD. It's the same, quite same as the Lumerical mode. And also, it should be noted that it doesn't matter. You can accelerate your simulation using Lumerical FDTD, because maybe you know that the Lumerical FDTD maybe need some more resources, and Ansys supports more HPC, more cloud, and you can enhance your speed with these items. And I will show you maybe in separate videos, and I will publish in YouTube how we can do that. Okay, so this is a Lumerical FDTD. It's the same as Lumerical mode and charge. So we defined our ring resonators. This is our solver. Our solver is FDTD. So we have a different port, top port, top left here, top right, bottom left, and bottom right. But in so for instance, for this specific case, we are interested to actually bottom right, because we want to calculate how much power coupled to the ring resonators. So for this reason, it's very simple. This is a very simple code that I can get the result, and I saved it to S, and then I saved to this file, And very easily I can use this file in other tools of numerical. So the other part also is same as the described here, like numerical mode, charge, and numerical interconnect. So thank you very much.